Welcome General Chemistry 151 students. My name is Madhulika Banerjee, and today I'll be talking to you briefly about the ideal gas law and how its variables affect particles that come into contact with one another. So you have two options as far as the simulator is concerned. You can either open it up on your own desktop and use that along with the podcast, or you can just watch the simulator that I'm about to bring up. So if you do want to access the simulator, open up a Google search page and type in Ideal Gas Law Simulator. Oh, there we go. And it should be the first link that pops up. It says Gas Law Program, and if you look at the URL, it's intro.chem.okstate.edu. Go ahead and click on that, and that will bring you to the simulator that we'll be using today. So this is our ideal gas law simulator. On the left-hand side, we have the simulator itself with all of the particles moving around inside of it. On the right top side, we have all of our different controls. So these are variables that we can change, which will affect the system that we have on the left-hand side. So as you can see, we have pressure, volume, number of moles of helium, number of moles of neon, and temperature. On the right bottom side, we have a graph that we'll be talking about later. Now the first thing that I want you to do is focus on the simulator and the particles within it. What do you notice about the speed of the particles? Are they all traveling at the same speed? Or are they traveling at different speeds? Are some of them moving faster while others are moving slower? Go ahead and take a minute, watch the simulator, and write down what you see. So as you can see, all of our particles are not moving at the same speed. Some of them are moving faster, whereas others are moving slower. But what if we want to watch the speed of one individual particle? Now, it's kind of difficult to do in the simulator with all of our particles moving around all the time, but something that makes it a little bit easier is this button right here that says Enable Tracking. What I want you to do is go ahead and click that button, and as you can see, it allows us to follow the movement of one individual particle. So now what I want you to do is watch this particle and observe what happens to its speed. Is it a constant speed, or is its speed changing? So it's very obvious that this particle has a speed that is not constant. Sometimes it's moving faster, other times it's moving slower. So we can take this idea and use it to describe all of our particles in the system. They're always changing speeds. Sometimes an individual particle will be moving faster, other times it'll be moving slower. But aside from making that statement, we want to know why this is happening. Why are our particles changing speeds? What I want you to think about is collisions. What happens when our tracked particle collides with another particle? In particular, what happens to the speed of our tracked particle when it collides with another particle? Go ahead and take a few seconds to watch some collisions and see if you can kind of conjecture what's going on here. So you can see whenever our particle is hit by another particle, there is a change in speed that occurs. Sometimes that collision will cause our particle to move faster, whereas other times it'll cause our particle to move slower. So what exactly is going on here? Well, whenever our particle hits another particle, there is a transfer of energy that occurs, and this transfer of energy can be seen through the change in speed. So if our particle is moving very quickly and it hits a slower moving particle, all of the energy that our tracked particle is carrying well, not all of it, but some of the energy that our tracked particle is carrying will be transferred to the other particle. Therefore, the second particle that was initially moving slower will now be moving faster, and our tracked particle will now be moving slower. So what about when our particle collides with the walls of the simulator? Is there a change in speed then? Go ahead and take a minute to watch, see if you notice any changes in speed whenever our particle collides with the wall. So our particle has hit the wall a few times now, and as you can see, whenever our particle hits the wall, there really isn't any change in speed whatsoever. So what does this tell us? Well, a couple different things could be happening here. One, there could be no transfer of energy whatsoever between our particle and the wall every time there's a collision. Or two, the transfer in energy might be so negligible that the change in speed isn't noticeable at all, and therefore for this purpose we can just call it a zero transfer in energy, and therefore a zero change in speed. Now what I want you to do is look at the red box that's moving on our graph. What does it signify? Is it showing us the average speed of our particles? Is it showing us the direction in which our particles are moving? Go ahead and take a few seconds to try and figure that out. So I don't know if anybody noticed this or not, but as our tracked particle changes speed, the red box on the graph moves. So what does this tell us? Well, it tells us that the red box is showing us the speed of our tracked particle. But what about all those other green boxes that are on the graph as well? What are those showing us? Go ahead and take a minute to see if you can figure that out. Just as the red box shows us the speed of our tracked particle, all the green boxes on the graph show us the speed of each individual particle in our system. One way that you can tell this is if you change the number of particles in the system. So let me increase it, and watch what happens. First of all, we get way more boxes. They're also going a lot higher. So what does this mean about the height of our boxes? What is that telling us? Well, the taller the box is, the more particles we have going at that speed. But what about this green line that's going down the middle of our graph? What does that show us? Go ahead and take a second, see if you can figure that out. So the green line in the middle is actually showing us the average speed of our particles. So remember, the boxes are showing us the actual speed of each particle, and this green line in the middle shows us our average speed of all the particles in the system. So as you can see, it tends to fall about in the middle of all of our boxes down here. Now granted, sometimes we can have boxes that are way out here that kind of throw off the average, but for the most part, our average speed line should fall in the middle of our boxes. So what happens when we increase the number of particles in our system? If you look at our graph, you see this smooth curved line that appears. It sort of resembles a bell curve, but not exactly. It's a bit skewed to one side. But what do you think that this curved line is showing us? Go ahead and take a minute, see if you can figure that out. So this smooth curved line is actually showing us the distribution of speeds for our particles. So what does that mean exactly? Well, most of our particles will be traveling at a speed right around here because this is the peak of our curve. And as we go to lower or higher speeds, we have less and less particles that are traveling at those speeds. Something interesting to note is that our average speed line is actually higher than where the majority of our particles are traveling at as far as speed is concerned. So that's something interesting to note. Aside from that, that's pretty much all for today. But definitely go ahead, mess around with the controls, see what kind of things happen to our graph as you change the different variables in the simulator. I hope you all enjoyed, and thank you so much for watching.